Hi there again. Wow, we're up to episode 11 of this series of solar and battery training. Today we're going to be looking at things such as calculating the VA maximum demand for a inverter for a standalone power system and understanding load profiles and how that can help us size a system. Also looking at string over current protection, mismatched arrays on the same Mppt, and how we calculate the maximum voltage of a PV array under cold conditions. All right, let's get into it. That's great. All right, well, we're up to episode 11 of this 13-part series called Solar and Battery Training. Wow, it's been quite an experience for both of us. First time we've done a really big webinar series. Normally we just do one-offs. And the purpose of this webinar series was to talk about how you design, as I said in the title, a solar and battery storage system, whether it's off-grid or on-grid with backup. We got to the point the day before yesterday where we talked about sizing for energy demand. Now, there's two main considerations in a solar battery system. It's in terms of what the loads require. It's how much energy they require, whether it's per day or over a longer period. But it's also how much power the loads require. So today we're going to kick off with talking about what's technically known as VA maximum demand. Now, for those of you, particularly electricians, will be familiar with this calculation from AS/NZS 3000, but it's actually quite different when you're talking about a standalone power system. The difference is that a standalone power system is actually a very limited supply generally. You don't have an infinite supply of amps like you do when you connect to the grid or just up to the capacity of your main switch. You have a limited output, and that's determined by your inverter. Sizing your inverter, if money is no object, you could just make it as big as you like, and you'll never have to consider any headroom limits on VA demand. But from an economic point of view, you generally want to choose something that's going to do the job, but at a reasonable price. Now, straight away I saw a question, what's the difference between VA and watts? Now, I'm not going to get into electrical engineering level explanations, but watts is true power, actual work done. VA is volts times amps. Now, volts times amps sounds like watts. It's true in a resistive circuit, but when you have a circuit that has reactive components, there's a certain amount of current that circulates around that does nothing useful. Sometimes it's jokingly referred to as the froth on the glass in your beer. The froth on the beer in your glass. It fills up your glass, but it doesn't really get you anywhere. That's what the reactive power components are. And so VA is a way of representing the amount of volts and amps, and the power factor is that useless part of the circulating current. Or it's actually out of phase current. I'm going to share a screen now so we can talk about this with some numbers. So just hold with me while I bring that up.
And so after that, Glenn, do you end up with watts after the froth and the froth's taken out?
That's right. Once you take out the froth, you end up with watts. But the problem with power factor is you still have to have a glass big enough. Otherwise, all that froth pours over the side and you get wet hands. So I think the analogy starts to run out at this point. So what you're looking at here is a table that I've drawn up. Now this table is actually from Appendix A of AS/NZS 4509.2. Now Rachel will probably put that in the caption. That's the standalone power system design standard for Australia and New Zealand. It was last published in 2009 and 2010, for 9 for install and 10 for design. It's a very useful standard, but it's got like an engineering grade calculation. So something like 16 pages of formulas. So I've really, in this presentation and in the one previously on energy demand, I've dumbed it down a lot. But I want to give an example here of how we consider sizing of an inverter based on the particular loads and their power characteristics. So what we've got here is a real installation. Actually, this was someone one of my students who had a particular project. When I run my face-to-face courses, hopefully I'll get back to those once COVID's over, we do practical exercises in the classroom, and I prefer if people use their own projects. So this was a project for a park in a school, or sorry, no, public park, which had a toilet block. And so they wanted it to be a solar-powered toilet block running off an inverter and battery system. So there's only 5 loads in this design. There's a water pump, which only operates at nighttime. It basically fills up a header tank. There's a sewer pump, which circulates during the day. There's a building management system, which basically controls things like lights and the pumps. There's lights, and there's an inverter, which operates all the AC components. Now, the first step in doing a VA maximum demand calculation for standalone is to find out what the power rating in watts of the appliances are, and find out what the usage times are in hours. Now, you'll notice that I've got 2 columns, a winter/dry and a summer/wet. Now, this is following the principles of 4509, which is to consider seasonal variation. I mean, you could get right down to monthly variation if you wanted to, but seasonal variation is sufficient generally. Now, so winter, summer would be for temperate locations, and wet, dry for tropical. So the reason for doing those 2 is to try and find out which is the worst case, which has the worst load resource ratio. Now, we'll get onto that in a bit. You'll notice I put in the column energy, and that energy is a calculation based on hours times power. So 500 watts for 3 hours is 1500 watt hours. It's a small unit. You could change that to kilowatt hours by dividing by 1,000. Now, if you move across a little bit, over to PF, you'll notice there's a column, PF. Now, PF, power factor, is that froth I was talking about. It is the kind of useless part of the energy equation, but you have to consider it because you still need to deliver those amps, even if they're not going to be doing any useful work. And so the power factor has an impact on the VA continuous demand. So what looks like a 500 watt pump with a power factor of 0.75, we divide 500 by 0.75, we come up with a VA demand of 660 VA. Now, we'll show how this relates to inverters in a minute by looking at an inverter data sheet. So actually, if we just went for a 500 watt inverter, it wouldn't be able to deliver what the load required. It actually requires 666 VA. But worse than that, much worse than that, is what we call the surge factor. Now, surge factor is because particularly things like pumps, when you turn them on, there is a very large inrush of current. And that inrush is due to the nature of the load, which in the case of a motor is virtually a short circuit until it starts to rotate and produce some back EMF. So it starts off as an inrush current of up to, in this case, 7 times its run power. So there's a huge amount of inrush. And we need to be able to deliver that, otherwise the pump won't start. So we're looking in the last column over here, we multiply 666, funny number, by 7, and we come up with, if I've done my maths right, 4,662 VA surge demand. Now that's an instantaneous figure. Surge demand is generally considered to be seconds, not hours or minutes even. It's just seconds to start an appliance. And you notice that I put a little star next to 3 of those items. Now, the recommendation in 4509 is that you identify in your load sheet coincidental loads which are designed to run at the same time. And that, therefore, your system must be able to run those 3 things with the red star next to them. I mean, the reason I haven't put a star next to everything is that I know that the water pump and the sewer pump don't run at the same time. One runs during the day and one runs during the night. So I don't actually have to be able to run both of them at the same time. And that's going to make a really big difference in the size of my surge demand total down the bottom here. My surge demand total is only 4,746 VA because I don't actually have to consider the sewer pump as part of that because it's running at another time, at nighttime. So I can see the questions are coming in, Rachel. Let's jump into some questions.
Yep, we'll start with a comment from Richard that directly relates to what you're talking about. On power factor, he said, while the froth does not provide useful work, it does have a use. For example, the magnetizing current required to run an induction motor.
Thanks for that, Richard. Yeah, look, there is some loss in the simple analogies. So for those who understand the electrical engineering behind reactive power, yes, you're correct, Richard.
Okay, these are a little bit, these are about batteries, and slightly off this slide, Chunyu asks, how much does Power Grid buy the electricity energy from the customer of solar power generating? And in the case of yesterday, how much can the customer save if he didn't use the battery system? In yesterday's case, battery is chosen was 15 kilowatt hours. If I limited the battery operating time, cut off the battery before 10 p.m, say, only provide 4 kilowatt load in the evening, can I choose a smaller battery?
Wow, Chunyu, it's a really complicated way you phrased that. So I don't know if I can even answer that usefully. I would suggest you have another look at yesterday's webinar, which is on my YouTube channel. But I did point out in that webinar series, that webinar on sizing for energy demand, that it's based on the principles of 4509, which is very extreme. It basically assumes that there is no renewable input during the days of autonomy, effectively a total eclipse. So you've got to run totally day and night off a battery system. There are all sorts of tricks, you know, such as turning off and controlling loads so they only come on when the sun's shining. All of these things can help reduce the size of your battery. But those are kind of more sophisticated solutions. I'm trying to keep it to the basic principles of energy in, energy out. So sorry, I can't answer that question as you phrased it.
Okay, thanks, Glenn. And Sean asks, which lead acid batteries don't need equalization?
Once again, this was something we covered way back in about episode 2 or 3, I think. We talked about charging characteristics of different batteries. Now, the terminology is not really, you know, specifically very clearly defined, but equalization generally means that it comes from the lead acid world, a certain amount of controlled voltage charging. So you don't exceed a certain voltage for a certain period of time and let the current drop away over that period. So typically equalization will occur over about a 1 to 3 hour period for a lead acid battery. Equalization is part of the healthcare system for a lead acid battery. You don't equalize a conventional lead acid battery, whether it's sealed or flooded, you'll cause sulfation. But there are some so-called advanced lead acid batteries which have characteristics that are more tolerant of intermittent equalization. So sometimes called a refresh cycle. It might only be once a month. So I know that the Occult Ultraflex I have here, it has periodic refreshes. I think it's actually once a week, but it doesn't have to be equalized every day.
Okay, and Mike asks, Glenn, can you please explain more how you got the 666?
Yeah, sorry. I should have pointed at it while I was talking about it. I'll go back to that. Okay.
And also for the surge of a motor, can we use soft starter or VSD to avoid high surge?
Right. So I'll answer the first question. If you look at the power demand, it's 500 watts. And if we divide 500 by the power factor, which is 0.75, it gives us our VA demand, 666. Second question from Mike was about reducing surge by using a VSD or short for variable speed drive, or sometimes called a frequency. Variable frequency drive. Soft start is a great thing to have in motors. It generally makes for better life, better performance, but it does add cost because VSD is effectively an inverter. It rectifies the AC, reinverts it, and changes the frequency and to some extent the shape of the waveform. That means that you don't get a surge. So you can cut that surge demand to almost nothing. It'll just be the rated power of the pump. In fact, even better than that, Mike, and I'm a big fan of VSD pumps for off-grid, is you can massively oversize your pump and hardly ever use that power. So I've got a 1900 watt Enviro something pump, because I can't remember its particular model name. It's a 1900 watt pump, but it actually runs at about 100 to 200 watts most of the time because that's all the demand the water needs. And so the VSD operates at very low power levels. So that means you're actually saving on wasting energy by circulating high bursts of power through your cables. Any other questions there?
Yeah, comment on comparison of lithium and lead acid. So if
Yeah.
there's space is not an issue, where do you see the cost-benefit balance here? If shopping today, would you buy lead or lithium? I think there's a few other things to consider here.
So thanks very much, Anonymous. Now that's a perfect segue to what we're going to be covering tomorrow. Tomorrow, we branch into another area. I've got a guest presenter who's a lithium battery expert. He understands a lot about all battery type, or lead acid and lithium batteries. So that's Simon Chan. So Simon Chan is my guest tomorrow, and we'll be talking everything lithium, right down from chemistry, safety, battery management system design. But to answer your question right here and now, if you do a usable kilowatt hour pricing calculation, really lithium's at a similar price to lead now. So, and it keeps going down faster than lead. So it's really, it's cost competitive. There are other factors to consider like temperature, whether it needs to have a particular management strategy, and that might limit the inverter or charge controller options available to you. So there's a little bit more complexity around using lithium than lead, but in price-wise, I don't think it's a big choice anymore.
Thanks, Glenn.
Okay, right. So just finishing off on this maximum demand calculation screen. And for those who haven't come to any of these webinars before, all of these slides I put into a PDF and share them on my YouTube channel. In the description, there'll be a link to a Google Drive folder or file, and you can download them from there. So down the bottom of that chart, if you look down those yellow boxes, you'll see there is a half-hour maximum demand, and it's based on what I call the continuous rating, allowing for power factor. In the case of appliances that have no power factor, I put a dash. Actually, I should have put 1. If you're doing this as a spreadsheet, that would be 1 because it's got no impact on the watts are the VA, doesn't change. So if all of those appliances were running at the same time, that's the amount of VA demand that the inverter would have to deliver. Now, the reason it's called a half hour, or in the design you choose to do a half hour, is that this is more likely to be the load on the inverter. Because inverters, when running sort of residential loads particularly, will have things coming on and off all the time. And so it's unlikely that at any one moment everything's on at the same time. But over a half-hour period, there will be an average amount of demand. So this is trying to say the average amount of power in a half hour could be around about 1,800 VA, and the inverter needs to be able to deliver that continuously at its half-hour rating. Whereas the surge demand is that peak that'll only occur for a few seconds, so it needs to be able to deliver that peak. In the old days, inverters weren't that powerful. Like when I say the old days, I've been installing off-grid systems since 1991, and a 2 kilowatt inverter was a pretty common size to have off-grid. I couldn't run my washing machine with anything else on. So I had to turn off everything in the house before I could start my washing machine, because the VA demand was at the maximum of that inverter. These days, inverters have got a lot more powerful, and also they have generally, ones designed for off-grid have very high surge ratings. That means their continuous rating might be 5 kilowatts, but they can surge to 10 or 12 kilowatts for a few seconds. Okay, so I see a question. I'll answer this one. Rachel, Sean's asked, should 80% DOD be considered in a number of days of autonomy? Sean, yes, it was. So if you go back to episode, what are we up to? 11, 10, 9, episode 9 on the YouTube channel, you'll see that the DOD is part of the formula in calculating the battery system sizing. So I won't repeat stuff that I've already covered. I'll just point you back to those slides. Now I'm going to jump over to look at a load profile just to show you why in a standalone power system or a system with backup.
Then there's just one question that has popped up relating to that slide you were just on.
Yep. Oh, okay.
Sorry. Jeremy asks, why isn't the surge demand 5 kVA when the sewer pump turns on?
Okay, so I'll go back to that. Thanks, Jeremy. Now, notice I put those little red stars. This is the recommendation in AS 4509 Part 2 for design of a standalone power system, is you identify the coincidental loads. You could just say everything has to run at the same time and the inverter has to be big enough. So in that case, the surge demand would include the 5,000 VA of the sewer pump and the 110 of the lights. But that would mean I'd probably have to double the size of my inverter. And the economics might not make sense when I know from practice of this design that the sewer pump and the water pump are mutually exclusive. They don't run at the same time. So one runs at night and one runs at day, and they're controlled by the building management system, so they can never run at the same time. So that's why it's not considered as a combination.
All good.
Okay, all right. So I'm going to show you another slide. Where are we? Bring it up. Okay. And where's it gone? Sorry. Got a lot of screens open at the same time. Got it. All right, here we go. So what you're looking at here is a load profile over a day. So midnight on the left to midnight on the right. This is actually my house, and I've got a power meter. I've got three-phase supply, so hence there's 1, 2, 3 plots on here. I've got a power meter that's measuring those three phases. Take a look at the bottom of the graph. You can see a little, almost like a square wave running across the bottom. That's the fridge turning on and off. It's interesting, you can really tell a lot by looking at a load profile. You can see some appliances and see their cycling. So I can tell what the duty cycle of my fridge is. It looks like about 30%. So 30% of the time the fridge is on. But the reason I'm showing you this is that if you have access to an ability to measure in real time, and this is, I think, 15-second resolution data, I can see coincidental loads. And if I do it over a longer period of time, I can scan back through and see what the coincidental loads are. So the highest individual peak here on this three-phase system is 2.2 kilowatts, which is probably my dishwasher coming on. It's a heating element. And you'll see it drops down at about 1600 hours. That's because it's heated the water and now it's just swishing it around. But there are also, on the other two phases, some loads as well. So I need to add those in there. So I'm probably going to get up to close to 2.5, 2.6 kilowatts of demand of coincidental load. So this is a useful design feature, is to be able to measure stuff before you actually build it. It's a bit of a luxury if the system hasn't got any appliances yet. Someone's just telling you what they're going to get. But if you have the opportunity to measure, you can get a lot of information about their loads. Okay, do we have some questions?
Yeah, we've got a couple. Greg asks, should you take the worst case scenario in regard to surge demand, i.e. the sewer pump and lights at night have a higher surge than the daytime loads?
Okay, so this will be specific to the installation you do. Like I said, as a designer, you can identify the coincidental loads, but of course they should be realistic. For instance, I've got a dishwasher and I've got a pressure pump. Now the chances are they'll both be on at the same time, because the dishwasher is going to draw water and the pressure pump will come on. So they're going to be coincidental demands. But I may put in my design that you can't use the arc welder at the same time as you're washing the dishes, and that's part of my design recommendation. And 459 even has in the Appendix A a column where you put notes. So you can put some notes about what appliances can run simultaneously. So yeah, the worst case might be that. I just kind of randomly put some stars on those.
Okay, and thanks, Glenn. Richard asks, do the maximum demand allowances from the off-grid standard that you described just then correlate to those in AS3000?
Richard, I don't know if you were in at the beginning of the webinar, but I was just pointing out that it's actually quite different off-grid than on-grid, because on-grid you've got a huge capacity from the grid in terms of instantaneous surge. Even if your capacity control is a 60 amp circuit breaker, for instance, you can draw way more than that. But inverters often have much harder limits, and so your maximum demand is on real maximum demand, not maximum demand after diversity calculations that you would use in AS NZS 3000. Any more questions?
No, that's good to go.
Okay. All right. Well, I'm going to change topic. I'm going to start answering a bunch of questions, and I picked these ones which is part of the design considerations in a PV battery system. But I picked these particular topics based on what I see a lot of questions, particularly on user forums online. And I thought I'd address them as the most common concerns or questions. So we're going to start with what's known as string overcurrent protection. And I'll just make this nice and big so I can see it all. And share my screen. All right. So what I've drawn here is on the left, a single string of panels. The dot, dot, dot means lots of panels. So it's a single string of panels. These panels have a short circuit current of 8.9 amps. That's from their data sheet, written on the back of the module too. It's part of the compliance label. And they're connected to PCE. Now, if you haven't heard that term during this series, it's a generic term for anything that modifies voltage, frequency, or current. It includes inverters, charge controllers, variable speed drives, anything, or switched or pulse width modulated charging devices. So PCE, think of it as an inverter in this example. I've also shown some isolation it also showed some isolation in the diagram. But let's just focus on the current. The requirement in AS NZS 5033 is that your array cable is capable of carrying 1.25 times the short circuit current of a string or of the array. And in this case, there's only one string. So we just need to size that cable for at least 1.25 times the ISC. Now you might wonder why there's no circuit breakers in a grid tie system between the array and the inverter, though you can use circuit breakers for isolation, but they're not required for overcurrent protection in a single string system, nor are fuses even, because there's no purpose to it. A PV module is a current limited source, a hard current limited source. And so its operating current is often only about 5 or 6% lower than its short circuit current. So in a strange way, your cable selection is your overcurrent protection. If the cable can carry the fault current, you don't need any overcurrent protection devices. So this is really just showing isolation, no overcurrent protection. So in a single string system connected to a PCE that has no battery, DC coupled to it. So I'm showing a PCE that's an inverter actually, so there's no possible backfeed from a battery. Next slide. Let's show the current flowing around. Now that circle just shows that the current's flowing through the PCE back through the array. And let's imagine that the PCE's gone faulty and we do actually have a short circuit. Even now there is actually no thermal damage to the cables or the panels because they can carry their short circuit current. But what happens if, scroll up, we add a second string in parallel? Now, if we add a second string in parallel, we covered this in episode 2 or 3, that we double the current potential of the array. But I've added one more problem. I've added a fault to this system. I've thrown an earth fault within one string. And because it's a floating system, I've thrown an earth fault somewhere else in the array cable. And that means now that the current doesn't all go through the PCE anymore. Some of it's actually going to flow in reverse into that faulty string. So the question is, do I need to have overcurrent protection to protect that, that string from that reverse fault current? So let's have a look. There's the current flowing in reverse through the good string, which is on the right, into the faulty string in reverse direction. Now, modules are actually rated for reverse current. It's sometimes called a series fuse rating, but technically it's a maximum reverse current rating. And so a panel can carry current in reverse, and it will just warm up. So basically it will heat up as the current flows in reverse through it. It won't produce any energy, so the faulty string doesn't contribute to its own demise. It just basically becomes a load. So in this example, the 8.9 amps that's coming out of the healthy string, the non-faulty string, is flowing into the faulty string. And because the faulty string can carry its own current normally, it's not going to cause any damage to it. So we check the data sheet, and it says on the data sheet that as long as you protect the module with up a 15 amp overcurrent protection device. That's up to, so a maximum of 15 amp overcurrent protection device, no thermal damage will occur. The cables, plugs, panel won't be thermally damaged. So even though we've got 2 strings of panels and each panel is capable of producing 8.9 amps, the faulty one doesn't produce anything. So it's absorbing 8.9 amps. So still, we don't actually require any string overcurrent protection device. So you're thinking, well, why do we need one at all, Glenn? Well, it's all about the numbers. Let's add a 3rd string in parallel. Now, I better say straight up, it's not about the number of strings. It's about the ratio of the n-1 number of strings times the short circuit current. What do I mean by that? To the series fuse rating. If I've got 3 strings and one's faulty, n-1 means I've got 2 good strings. 2 times 8.9 amps is 17.8 amps. So I've got 17.8 amps of current, which could flow in reverse into that middle faulty string. The series fuse rating says that you cannot pass more than 15 amps through a module in either direction without causing thermal damage to it. So at this point, I've triggered the requirement for string overcurrent protection. I've got to protect that any one of those strings from more than 15 amps, because it's possible to get that from with the single fault in one string. So you need to look at ISC and series fuse rating, subtract 1 string, multiply it by the number of good strings. Is it more than the fuse rating? If yes, in go the fuses. So there's the formula from 5033. 5033, it's actually got a little bit more to it, this formula. You can't have it too small. See, if you are required to have string overcurrent protection, it's got to be at least 1.45 times the short circuit current of a module. The reason for that is to prevent false tripping of protection devices due to high radiance, high temperature of protection equipment, and even just manufacturer's tolerance as well. If any of you remember the earlier versions of 5033 back in the 2012 edition, 2012 or the one before it, 2005, said 1.35 times. We discovered that at 1.35 times, there was still a certain amount of false tripping occurring in practice. So we increased it to 1.45 times. It can be up to 2.4 times the ISC of a single string, but it has to be less than the series fuse rating. So generally, you'd never get to 2.4 times unless you've got some panels which have massive series fuse ratings. Generally, they're around the sort of modern panels around the 15 to 20 amp these days. So what do? We put in some fuses. And the wording in the standard says that, doesn't say fuses, it says overcurrent protection devices. So it says they must be as close as practicable to the point of combining of the strings. And so where the strings come together, that's where you should have your overcurrent protection devices. You need them on all unearthed poles. So most arrays are floating these days. So that means both poles need to be overcurrent protected. Why would you use a fuse? Because I've shown fuses here as opposed to a circuit breaker. The reason is cost and performance. Circuit breakers don't necessarily have the right trip characteristics for a PV array. A PV array doesn't have a high inrush current when it has a fault. So it has a small peak that lasts many hours during the peak of the day. So there are fuses specifically designed for the characteristic of a PV array and fault. Then the fuse type's known as GPV, so the categorization of those fuses, and they suit that slow overload condition. They're also much cheaper than using circuit breakers, but you do need to put them in some sort of holder generally. There are such things as inline holders for some types of connectors too, but generally it means another enclosure, some fuse holders and some fuses. So how are we going there? Rachel, any questions?
Yeah, there's about there's more now. Lewis asked if the IEC rating came into fuse selection.
Sorry, can you repeat that question?
Lewis asked if the IEC rating came into selecting the fuse.
Actually, I don't even know the answer to that question. Sorry, that's one I can't answer on the spot. Next one.
George asks, are there any issues that can arise by installing string fuses on earthed poles?
Uh, well, no, but you don't have to. So I guess the standard just exempts you from having to have overcurrent protection on an earth pole because it's trying to interrupt an earth fault. So if you've got a fuse that's on the earth pole and you provide an earth on the earth pole, it makes no difference. So in a way, looking at this diagram, if this was an earthed PV array, the right-hand fault, which is that little red earth symbol, would always be there because you'd choose to earth it. Now, earthing of PV arrays is another whole discussion. It's very rarely done in grid tie systems anymore. The reason for that is transformers inverters. You cannot have functional earthing on a transformers inverter. It will blow up. So it's got no galvanic isolation between the input and the output. Earthing of arrays does save you one pole on a switch and one fuse if you required fuses, so the very small cost benefit. But there is generally more risk because now you need only a single fault to earth anywhere in the system and you'll have a fault current. Whereas here I needed 2 faults. So yeah, earthing's not very common unless it's for galvanic protection.
Okay, Dennis asks, fuses have a fusing factor, as do circuit breakers. Do you take this into account when sizing the fuse, or is this just an overhead that exists?
So I mentioned there's a type of fuse, GPV type. So fuses come in different characteristics. So there's like GR for semiconductor, GG for general purpose. GPV is where the fusing factor suits the characteristic of overload in a PV system.
Okay, Mohammed asked if you can use diodes in series on each string to protect them against current flow and also short circuit.
Thanks, Mohammed. The short answer is no, but they will help. So using what's known as blocking diodes are not deemed to be a safety device. Diodes can often fail short circuit due to thermal overload, due to voltage spikes from lightning, etc. So they're not a reliable air brake device like a fuse or circuit breaker is, but they will stop this reverse current flow until they fail. And so using blocking diodes, which imagine instead of those orange fuses that I drew, so I'll just bring that picture back up. Instead of those orange fuses, you had blocking diodes, then you would prevent that reverse current flow. But now you've got another problem, particularly in an LV system, you've got fuses, you've got diodes which are going to get hot. They're probably going to need to be on a heatsink. That heatsink would need to be double insulated. You start to get a lot of cost going into this. It's still used in some countries in combiner boxes, particularly for large scale systems, but very uncommon in a commercial or residential system.
Okay, there's a few more questions. CR asks, why use fuses at both sides of the string and not only one?
Because we don't know which way the fault will flow. So I've shown the earth fault near the inverter on the negative leg of the inverter. If it was on the positive leg, the current will flow the other way. So we just don't know exactly where the current path will be.
Okay, sorry, it's great if you can ask questions as you think of them and not when Glenn's talking, otherwise they may not get answered. It's easier to answer them if they come in, regularly. This one goes back a few slides, I think, and sorry if you've answered it, Glenn, but someone just asked about the 15-second monitoring resolution for surges. Is that 15-second a bit too long? Because surges occur quicker than that.
Well, in a way, I'll come to this when I show you a data sheet for an inverter and how they rate that surge demand. It does depend on the appliance, the inverter, what its instantaneous peaks are. So let me answer that by talking about a particular inverter and looking at its data sheet. But I can see a question there that I'm dying to answer because it's actually in my presentation, which is from Anonymous. I'll read this one, Rachel. I received a quote for a 17-panel install, but their proposal shows they would put in 17 panels, 9 facing east and 5 facing north and 3 facing west. Can you explain how this setup works? All right. Well, it may not, Anonymous. It really depends on what equipment they're using. So let's just jump into the next topic, which is multiple orientations of an array on a single Mppt. So I'll just bring that up now. And I'm just having a little problem here. Right, great. I'm going to draw live here. Hang on, I've shared the wrong screen, sorry. There we go. Okay, you should see a nice blank screen. I'm going to do a plan view of a house with, there's a center line of the roof. And so this is east, and this is west, and this is north. So it's not exactly the design that Anonymous mentioned, but I'm going to keep it rather simple here. And so they're going to put a bunch of panels on the eastern side. There's 8, and we're going to put 8 panels on the western side. We're going to connect them to an inverter. Now, here's my inverter over here. What is very popular in residential inverters these days is what's known as dual maximum power point trackers. What that means is there's 2 inputs to the inverter so that each string, and a string is a series connection of panels, can be different. I don't actually have to have identical strings. I can have different numbers. So you might actually have, 9 on one roof and 7 on another. That will work just fine as long as you're within the voltage window of the inverter on those strings. But there's another option, and this option is allowed under 5033, and surprisingly it works. And I'll just draw that one. If we join these 2 together, so we've now paralleled, whether it's on the roof or down at the inverter, it doesn't matter. We've paralleled 2 strings, but the rule is they must be the same number. So we've got 8 modules on this side. We've got 8 modules on this side. So they must be the same number, same type, and on each string, they must be facing the same direction, plus or minus 5 degrees of azimuth and inclination. So that means all the eastern panels face the same direction, east. All the western panels face the same direction, west. They can be paralleled, and this will work just fine. Now, the question I often get as a follow-up on this one when I show this is, oh, yes, Glenn, sure, maybe it works. Sure, you're allowed to do it, but is it a good idea? Wouldn't you be better off using a dual Mppt? The answer is it depends. If there is no shading issues on either side of those roofs, actually the performance difference is very small, less than 1% benefit going for a dual Mppt. So there isn't actually a big performance reason to use dual Mppts, but there is some caveats around this. As soon as you get shading on one string, you will have a mismatch in voltage and get poorer performance out of the unshaded string. So this design really only works in an unshaded roof arrangement. It doesn't have to be east and west. It can be north, south. In fact, it can be east, north, and west, as long as all 3 surfaces have the same number of modules and they're parallel together. But you also need to consider the maximum current input of your PCE, your inverter in this case. Can it actually carry 2 strings of current, or can it carry 3? That will be a consideration of the design. People still doubt me when I say this. They go, it can't be true, Glenn. Surely the sun's going to be shining on the eastern panels in the morning, and they're going to be working really well, and they're going to drag down the western panels because they're in partial light. They're not in direct sunlight. They're in diffuse light. Well, there's a lucky bit of physics that happens. The voltage of a PV panel increases with irradiance and decreases with temperature. And what do you know? Those 2 things cancel each other out. So as a panel gets more sun, it heats up. So the sun is kind of the irradiance, notionally pushing up the voltage, but the heat of the sun causes the voltage of the panel to reduce, and the 2 counteract each other. So over a day, the panels on the side that aren't getting direct sunlight are operating at almost the same voltage as the panels that are getting direct sunlight. So the voltage mismatch is minimal. Now, if you still don't believe me, both SMA and Fronius have written academic papers on this and proven it. Now, both those companies sell dual Mppt and single Mppt inverters, so there's no commercial reason for them to try and push this. They're just pointing out that it is a lucky coincidence of physics. Okay, a bunch of questions have come in, I can see.
Yeah, I'll start with the three that have been waiting. Miguel asks, can you clarify your statement re-earthing of array, please? Were you talking about the frame or the cables?
Sorry, when I say functional earthing, that means the conductors, the current carrying conductors being bonded to earth, not equal potential bonding.
Thanks, Glenn. David asks, are DC surge diverters worth installing in lightning prone areas?
Thanks, David. There is actually a lightning standard in Australia and New Zealand, and that standard is a risk assessment that you are required to do, and the risk matrix will tell you whether a lightning protection system is mandatory or optional. Now, in a kind of just a really crude sense, unless you're up a tall building in northern Australia or on top of a mountain in New Zealand, it's unlikely that you would trigger that requirement, because we don't actually have a high lightning incidence in most of New Zealand and Australia, except for the Northern Territories, by the way. Sorry for those from the NT, you are the lightning capital of the world. But lightning protection can be put in just for insurance, so you really want to make sure that it doesn't fail. But that's never permanent, never perfect insurance, because lightning can still destroy lightning protection systems. So it's kind of like a good idea. It's often built into many pieces of equipment already. Things like metal oxide varistas or MOBs are often put across the DC inputs of inverters to limit small voltage spikes induced by lightning. But once you have a direct strike, it's extremely hard to interrupt that. Really, you have to divert it with a lightning protection system.
Okay, thanks, Glenn. David just mentioned granite belt. Does that make sense?
Sorry, the granite belt too, but if you look at the lightning standard, and also the flash map is in the back of 5033. It shows you the zones and what the flashes per square kilometre per hour are, and you can see if you're in a high lightning zone, and you can apply using the formula in the lightning standard to work out whether it's compulsory or not.
Okay, and John asks, back on string fuses, is it more practical to have those downstairs rather than on the roof?
There's two schools of thought. So combining on the roof often means less cabling because you've only got one array cable. So you're saving on cable runs, but it means that you've got to put a weatherproof housing often if it's up on a roof. So it's more expensive and more likely to sort of have moisture ingress. So, there's swings and roundabouts. Personally, I prefer to keep it off the roof. Less stuff that's up there that's going to get water in it, the better.
And George, referring to the east-west orientation or multiple orientations on one input, is this not an issue from a CEC perspective?
CEC, for those who are not familiar, is the Clean Energy Council, not to my knowledge.
Okay, and Doug asks, sorry, this just popped in. If you have your east and west panels on one input and then north panels on a second input, would you still be limited to oversizing a system by 133%, or could you oversize by more panels?
All right, so Doug, thanks for that question. This oversizing question, if you're not from Australia, just put your hands over your ears. It's all about our strange CEC guidelines. The CEC guidelines, I actually helped write them years ago, so I'm partly to blame. They were written as kind of rules of thumb that the amount of PV peak watts on the roof with respect to the AC output power of a grid tie inverter was deemed to be approximately 75%. So the AC output should be at least 75% of the peak watts of the array. And that was just so that you wouldn't have any clipping of the production of that array under normal weather conditions over a year. So it was about the economics, really. It's somehow, because of the way our rules work in Australia, they got to be rules as opposed to guidelines. And so if you're creating STC, small scale technology certificates, you need to comply with the CEC guidelines. Now, those guidelines only apply to grid tie systems without batteries. So if you're installing batteries grid tied or batteries off grid, that oversizing rule doesn't apply. Incidentally, It's normally referred to as the 133% oversizing, because that's the reciprocal of 75% output power of the inverter. That rule doesn't apply if you add batteries. But if you have no batteries in the system and you wish to create STCs, this is purely a economic regulatory rule. You must comply with that. The other thing you do need to comply with is the manufacturer's recommendation. So a manufacturer will often say you can oversize the DC power, and that's how it's referred to often in a data sheet, by 145%, 200%. I've seen 245%. What they're saying there is that it's fine to let the inverter clip. So I think I'll just draw this to answer this question a little bit in more detail. So let me just bring back my slide. There's a common misconception that you'll blow up an inverter if you ever have a PV array that produces more power than the inverter can output. And that's sort of basically wrong. It's assuming that the inverter has no control over the array, but the reality is the inverter does. The inverter is a smart load. Now let's draw an ideal curve on a sunny day. So there's an ideal curve. So this is power here. That peak might be, let's say, 8 kilowatts of peak power. Now that might only occur on a really cold day, by the way, because of course panels lose power as they heat up. And we connect an inverter that can only put out 5 kilowatts. So our 5 kilowatt inverter, well, let's say not out, but its input can accept 5 kilowatts. And that's generally a current limit as opposed to a power limit, though both matter because power heats up the inverter. So the inverter would do this. It would go poop, up. So it's actually not going to produce that bit up, that bit up the top there. It's going to clip it because it's controlling the current flowing into its maximum power point tracker. So it just chooses not to use the full power of the array. So you're not blowing it up. It's not dissipated as heat somewhere else. It's just not produced. But the ability for the inverter to operate for those extra hours, that might now be 5 hours of full power, is another issue because that increases the thermal load on the inverter. And that's where the manufacturer's recommendations are based on. They go, we just know what the thermal load on an inverter is designed for. It's designed for a typical solar day with 2 to 3 hours of peak power. If you exceed that, you'll compromise the warranty, you might cause it to fail thermally. So that's where that clipping comes in, and the overpowering rule is really just trying to stop that happening.
Okay, thanks, Glenn. And Vera Kumar asks if the 133% rule applies to a 200 kilowatt installation for LGCs.
Thanks, Vera Kumar. So once again, anyone who's not installing in Australia can cover their ears because this only applies to Australia. LGCs is large-scale generation certificates. There is actually no minimum size for LGCs, but in practice, no one bothers until you get to 100 kilowatts because that's when the STC limit is reached. So systems generally over 100 kilowatts will create LGCs. To create LGCs, it's got nothing to do with the CEC. You don't even need to be accredited with the CEC to create LGCs, just a licensed electrician installing the system and complying with Australian and New Zealand standards. So those LGCs have nothing to do with the CEC, therefore the 133% rule from the Clean Energy Council's guidelines don't apply.
Okay, this one just popped in from Richard. If the inverter clips the power, I understand that no additional heat is inside the inverter. What about on the module? Does the PV module heat up? Just looking at energy balance, sunlight in, electrical energy out.
Yeah, so in terms of current, because the inverter controls the current of the PV array, and it chooses what current to draw from the array, therefore the array is not actually producing any more current. When the inverter doesn't want it to, it doesn't have to dissipate that as heat. But there will be a certain amount of the fact that you've got photons hitting a PN junction, liberating electrons, and they're being reabsorbed again because not all the current's being required. There will be a little bit of heating, but it's from my observations, it's almost insignificant. So we don't have to, like a hot water service, a flat plate hot water service can overheat on a summer's day. That's not the case of a PV array. In fact, you can put a PV array out in the sun and put it into short circuit and leave it there, and it'll be quite happy.
Okay, I've got a question, Glenn, about the same different orientations on the same input. East-west seems fine, but what about northeast and southwest? Could I do that?
Yeah, so I just generally draw it like east-west because it's a very obvious mismatch, but any mismatch will still exhibit the same temperature characteristics and irradiance characteristics on voltage. So you know, it's the same as true of any mismatch array. You will still get a very similar voltage in both of those strings.
Thank you.
Okay, we've got about 4 minutes to go in this session, and I think we've run out of questions. Is that right?
Yep, for now.
Great. All right. So a question that came up in forums recently was about calculating the VOC max of a PV array, the open circuit voltage maximum. How high can it go, and how do you calculate it, and what are the regulatory limits? So this is to do with Australian and New Zealand standards. So the VOC, so voltage open circuit max, is the maximum under any operating conditions. It's not the nameplate rating of a panel. And in a residential system, we require that to be less than or equal to 600 volts. In commercial, you can go up to 1500 volts. So any non-residential can go up to 1500 volts DC. So that's the first thing. Is it a residential installation, or is it a commercial or industrial installation? How do you calculate that VOC max? Now, there are 3 methodologies that are given to you in 5033. You can calculate from the data sheet using temperature coefficient. So one is using the adjustment based on temperature. Now, with a PV array, with a crystalline module, the colder it gets, the higher its voltage goes. So you need to make an assessment on what is the coldest operating temperature of that PV array. And a good conservative principle is basically the coldest temperature ever. You can look this up on the Bureau of Meteorology. You can use table 4.1 from the standard. So table 4.1 of 5033 gives you some 5-degree temperature ranges that you can choose a multiplying factor. So I think 0 to 5 is 1.1 times from memory. I can't remember exactly, but you can use just the table and look it up. And method number 3 is if the manufacturer recommends a way of calculating. So the usual story, can't spell when I'm writing. So manufacturer's recommendation. So those are the 3 methodologies that are permitted in 5033. Now, some questions have come in.
Yeah, Sean just said, did I hear right? Can you really oversize more than 133% on a hybrid or off-grid system with batteries for STC purposes?
Yes, you did hear right, but, and this is the big but, you should confirm this with the entity that creates your certificates, because they're the responsible entity. So if they're happy to create certificates on a hybrid system with 150% oversizing, then of course you can do it. So just check with them first before you go ahead.
Okay, Anonymous says, I have a large south-facing roof, but limited in my northwest and east. Quotes from all companies I've gotten back never utilise the south and look quite ugly. Does this choice have something to do with STC, or why else would they do this?
All right, I love this one. There is this fear of the south in the Southern Hemisphere. Somehow it's dark and gloomy and scary. You know, it's sort of Game of Thrones territory. There is nothing wrong with a south-facing array. It's nothing illegal about putting panels on the south. They actually work in the south, but they work in different ways. I should go back to my diagram because I love this question, and I will actually go over time today. I normally don't do this, but I so much love this question. I'm going to go over time. So thank you, Anonymous. If you consider a roof now, here I'm drawing the roof again, but this time I'm going to make north at the top. So there's north and there's south. Depending on your latitude, if you live in southern Australia, the sun actually rises over here in the southeast in summer. So this is east over here. Bring my pen up, east and west, and it will traverse the whole day, go around the north, and then set in the west. So actually in the morning and the afternoon, the sun is in the south. So if you have a pitched roof, let's say a typical 23-degree roof, the sun doesn't even get to the north side of your house till about 9 o'clock in the middle of summer. Now that means south-facing array actually has a benefit to customers who use power at either end of the day in summer. Air conditioning in the afternoon, morning, making coffee and washing dishes, they'll actually be having more self-use of that solar rather than spilling it to the grid at less value. But if you've got batteries, facing it to the optimum angle will give you more energy. So you'll be able to store that and use it yourself. Or if you have a good feed-in tariff, spilling it to the grid and getting a benefit is still a good idea. But what does the north versus south look like? I like to sort of simplify it a lot. It's all about your latitude. And if you're concerned about south-facing arrays, just remember that a south-facing array, which is a facing away from the equator in Melbourne, is about as good as the best facing array in Germany. So if you're saying you can't put it on the south, then you shouldn't even install panels in Germany in any direction because they don't have as much solar radiation over the whole day. So yes, south works, but it will work much poorer in winter, and in summer it will work fine. In fact, it'll make no difference almost in midsummer in northern latitudes of Australia because the sun's straight above you. Thanks everyone for turning up for today's webinar. Tomorrow, we're going to be doing something different. We've got a guest panelist, Simon Chan from Power Plus Energy, and he's the expert on lithium batteries and battery management systems. So tomorrow is all about lithium batteries. Hope to see you there.